All right, this section is the bread and butter of calculus. So basically, derivatives, everything you do in the first half of the year is all about derivatives. Once you understand derivatives, then everything else becomes quite a bit easier. Now, we're not going to go, we're just getting the introduction. We're going through the kind of the hard stuff of derivatives, actually. I mean, some applications that you'll learn next year are harder, but you'll actually learn some tricks that make things a little bit easier next year. But the key is understanding what the derivative means, and that's what we're going to focus on in this section here, is understanding what the derivative means. Now, first off, if you've heard like the term derivatives in terms of like the I don't know, the housing crisis back in '07 or whatever, the financial crash, this is not the same as that. So derivatives can be used in business as in the mathematical sense, but usually when you hear about derivatives in business, it's usually referring to something completely different. However, again, like if you've ever heard of marginal cost or you know, like we have a marginal tax bracket, that type of thing. Um, like the marginal cost is the derivative of total cost. So that is the mathematical sense. So it does happen from time to time. But derivatives are used in everything. Like they are a very important discovery, and we're going to kind of go through the process of how they were discovered, kind of mathematically at least. And yeah, so derivatives, like the derivative, if you're in physics, the derivative position is velocity, derivative velocity is acceleration, the derivative of acceleration is called the jerk. Um, Derivative of charge is current. There's all sorts of different derivatives apply in every single scientific field. I mean, anything, especially in physics. Like, or if you want to do biology, like predator prey models, those all deal with those are differential equations that deal with the derivative. You're talking about fluid dynamics. Well, that's all differential equations. So, you name it, and derivatives are probably behind the scenes somewhere. So it is a very important topic. It's probably about 50% of Calc 1 is all dealing with derivatives. So, anyways, enough of an introduction. Let's get to it. What is a derivative? So, first things first, average rate of change between 2 points. We've learned about that in the past. If you look at this little chart here, the average rate of change is basically the slope of this line. So if I have average rate of change between P and Q, would be the slope of that line. And that line is called the secant line. All right, um, so that's what our average rate of change is. And so again, we call that a secant line. Um, Now, the instantaneous rate of change is, well, what if instead of keeping this point Q here, what if we want to find out the instantaneous rate of change at at the point P? So instead of Q being here, well, what if we made it here? And then what if instead of here we made it here? And what if instead of here we made it here? So notice as we do that, um, it's got a nice picture down here. As we slide it down here, notice what's happening to these lines. So these are all secant lines. I'll erase them in a second, but those are all secant lines. But as we approach, as Q gets closer and closer and closer to P, it's going to approach what looks like the tangent line, and that's this guy right here. That one's the tangent line. So the tangent line just kind of touches at that point and then veers off. It's kind of one of the ways I kind of like to think of it is like if the sun were to disappear, what path would the Earth go on? Well, it'd go on the tangent line. It'd go straight from where it was going. So if there was some sort of force acting on this curve, if it stopped acting, it would just keep going. The particle would keep going in that direction. So the tangent line is what we're going to be looking for. So and realistically, luckily we have a technique we can use for figuring out how to have this happen. Um, how to get Q close to P, and that's going to be using the limit. So if I take basically as Q approaches P, um, that limit will be of the slope of that secant line will become the slope of the tangent line. So let's explore that a little bit. So um, the way we're going to define it is going to be using f of x plus h minus oh sorry at a sorry so it's f of a plus h minus f of a over h. And so if you think about it, what we're going to do, let's go back up to um, this picture right here. So what we're going to do is here's a plus h, and then the y value here, that's f of a, and this is up here is f of a plus h, right? Take a, plug it in, we get into our function, we get f of a. Take a plus h, plug it into our function, we get f of a plus h. So if you notice, this distance here is f of a plus h minus f of a, and this distance here is a plus h minus a, which is just h. So if we find the slope of that secant line, it is just f of a plus h minus f of a over h. So basically this formula that we were talking about over here. Now, the difference, what makes it a tangent line, is this limit as h goes to 0. So if we let h go to 0, what that's going to do is going to slide that point closer and closer and closer and closer and closer to p. So as h goes to 0, right, this is getting closer and closer. So this limit, slope of the tangent line, also sometimes called the slope of the graph at that point, and also called the derivative Let me make sure that that's what we're looking for at that point in time. Yeah, actually, I think before we introduce that term derivative, but that will end up being the derivative. But I think what we're looking for is instantaneous rate of change. Instantaneous rate of change. So again, one of the ways you can think of the secant line gives me my average rate of change. The tangent line gives me my instantaneous rate of change. All right, so let's find the slope of the tangent line to the graph f of x equals x squared minus x at the point 4, 12. So in this case, if we're looking at this, a is equal to 4, and then f of a is equal to 12, right? If we plug in 4 squared minus 4 gets me 12. So if I'm looking at this, I'm going to have the slope is equal to the limit as h goes to 0 of f of, again, a plus h. So a is 4, so 4 plus h minus f of 4 over h. Well, if we plug that in, plug 4 plus h in. So let me actually kind of color code this. So if we look at this guy right here, what that means is just take 4 plus h and plug it in here and plug it in here. So I get the limit as h goes to 0 of 4 plus h squared minus 4 plus h. That's all of that green box. And then we can do this in a blue box. F of 4, we already talked about that. That's 4 squared minus 4, so that's 12. So I have minus 12. That's all over h. So let's do a little bit of algebra here. Simplify it down. So limit as h goes to 0 of 16 plus 8h plus h squared minus 4 minus h minus 12 over h. And a lot of times if you want to, you can kind of drop the h goes to 0 and just write limit. It's just a nice little shortcut there. So notice I have 16 minus 4 minus 12. Those cancel off. Notice I have 8h minus h gives me 7h. And then, so I've used these guys up, and I still just have to do that h squared, so plus h squared. Now everything has an h, so I can cancel an h from everything. So I get 7 plus h over 1. That's a little messy. I can write it over 1 if you want. And that we know the limit as h goes to 0 of that. I plug in 0, I get 7, because that's a polynomial there. And so I get that limit is 7. And so that's our answer. Our slope is 7. All right, so that's kind of the algebraic way of what we're going to be looking for. So now, before we go further, I kind of want to pull something up and play around with it a little bit, so that way you can get a little better understanding. So let's just look at some function here. Again, we got this graph here. Now notice what I'm going to happen is I'm going to drag this pointer across, and we can see the secant line, right? All these things are secant lines. So this is, f of c plus h. We use a, so a and a plus h, same thing. But notice what the limit is h goes to 0. That means the distance between these 2 points is going to get closer and closer to 0. So what ends up happening is I keep on sliding, keep on sliding, keep on sliding. And then as I get really, really close, that's basically going to be the tangent line. Now, um, when it's on, notice it disappears because it's not looking at the limit. It's just looking at the value, and it's undefined at that point. But the limit will not be undefined. So if I show the tangent line, that dotted line, notice as I move this point closer and closer and closer and closer, it doesn't matter from the right or from the left, I get closer and closer to that dotted line. Similarly, from the left, I get closer and closer to the dotted line. So similarly, if I look over here, I get closer and closer to that dotted line. So that dotted line, the slope of that is called the derivative. All right, so it's the slope of the dotted line, not the dotted line itself. The dotted line itself is tangent line. The derivative is the slope of the tangent line, also known as the instantaneous rate of change. So that's kind of a nice diagram to show you that's what it's trying to show you in this little picture up here with all the Q's. So hopefully that helps explain it a little bit better. So when we take this limit as h goes to 0, what we were doing was sliding that point closer and closer and closer, and we found out that the slope of that was 7 for number 1. All right, let's go ahead and do number 2. So first off, remember point slope form of a line. Well, that's y minus y1 equals m times x minus x1. And then slope intercept is y equals mx plus b. Now, in general, I don't really care which one of these you use. You can leave it in point slope form. You can use slope intercept form. This particular question asks for it in slope intercept form, so we better do it that way. But in general, point slope form is fine with me. All right, so find the slope intercept equation of the tangent line to the graph of f of x equals square root of x at 1, 1. Okay, so first things first, now we're trying to find the equation of a line. In order to find the equation of a line, in particular in slope intercept, we need to find the slope, and we need to find the y-intercept. So how do we find the slope? Well, we know the slope is equal to the limit as h goes to 0 of f of a plus h minus f of a all over h. That's our definition from up above. Now f is square root of x. A is, let me write that from below, a is the x value here. And so what I'm going to do is I'm going to have equals the limit as h goes to 0 of, it's going to be square root of 1 plus h minus f of a, so plug in 1, square root of 1. I'll write square root of 1 for now. It's just 1. Well, so, let me go ahead and write just 1. Hopefully you can kind of follow that progression. And that's all over h. Now, we need to find this limit. If I plug in 0, I get 0 over 0. That's no good, so we need to do some algebra. So let's do some algebra. If you recall from last section, we had one with a square root in the top. And what did we have to do? We had to rationalize the numerator. So let's multiply top and bottom by square root of 1 plus h plus 1. All right, so now when we multiply that all across, I get 1 plus h minus 1 on the numerator, and I'm again just going to leave the denominator unmultiplied. I'm just going to leave it. I'm not going to distribute that through. So then on the top, I get just plain old h. And the h's cancel. Because I'm under the limit, I can go ahead and do that without any restrictions. So I get equals the limit of 1 over square root of 1 plus h plus 1. Now I can plug in h equals 0. So square root of 1 plus 0 is square root of 1, which is 1. So I end up with basically 1/2. So that's my m. So I've got that so far. So now I've got y equals 1/2. Again, that's from there. X plus b. And 1, 1 is on my graph, right? I'm going to use that guy right there. So I have 1 equals 1/2 times, did I say plus h? I meant plus b. Hopefully I said it right. But 1/2 times 1 plus b. As I write another h. All right, so now I subtract, I get 1/2 equals b. So I get y equals 1/2 x plus 1/2. So what I like to do is just to show you what we just did here and on Desmos to make sure we understand visually what's going on. All right, so we were looking for the tangent line at 1, 1 for the graph y equals square root of x. So if we've done it right, what we should have is something that looks basically, again, if you kind of imagine what the tangent line would look here, I can actually go ahead and do this real quick here. So I should have something that looks something like this when I graph it. So let's see if that looks, if when I graph 1/2 x plus 1/2, if I get that. And indeed I do. So that definitely looks like it's tangent at that point. So I think we did everything correctly. So I keep on using this term derivative. I actually haven't defined it yet, but when I talk about this slope of the tangent line, that actually is the derivative. So, and there's two different ways of thinking about it. There's a derivative at a point, and then there's a derivative of a function. So all this stuff up here that we did, both 1 when we found 7 and 2 when we found 1/2, that's finding the derivative at a point. So definition of the derivative of a function. Let y equal f of x denote a function f. The derivative of f at x, I don't, you can just say derivative of f, but this is how the book describes it. Derivative of f of at x denoted by f prime of x is defined by, this is going to be exactly the same as our definition up above. The only difference is now we have x instead of a.